Testing, testing. Okay. I don't know what the question is, but the answer is SpongeBob SquarePants. Very true. Anyway, good morning, class. Nice to see we've got a whole 44, 46. Oh, it's going up. 46 people logged in right now. Hello. To the question, can I please explain the bonus question in assignment 5 during the lecture? Nope, sorry, not going to have time, but please ask about that in your tutorial. We are just about a complete week behind here, and we gotta keep moving. So, unfortunately, that's just the way it is. So, very quick note with respect to sort of housekeeping stuff related to the course. Some of you may have seen the shameless self-shilling / plugging that I put up on the announcement feed yesterday. The MSU Teaching Award nominations are now open. There's a link there. I'm not saying you have to. I'm just saying, you know, it would be nice if you consider throwing a few bob at your favorite professor, and maybe some of the TAs too, because they work very hard for you guys. So with respect to that, the way I'm also telling you guys because like you guys might not know that this sort of thing exists. A lot of you guys, since this is a first-year class in the first semester of your first year. Essentially, the MSU Teaching Awards are a way that the McMaster Student Union, which you've probably had minimal interaction with because most people do, they have this thing that they give teachers awards for being good teachers. It's generally speaking, the people who win the award are selected by a combination of the number of nominations received from students and the scores that you score the class on your teaching evaluations. And yeah, anyway, I'll say no more about it, but you know, it would be nice. I kind of feel like this might be my semester, but you know, we'll see. Anyway, so let's continue to talk about floating point numbers. So last time we sort of ended on this idea that equality comparison with floating point numbers is completely unreliable and you should never ever use it. This is a completely true thing. We can demonstrate very easily that you should never do this because sometimes, oh my goodness, sometimes you might have something like this that looks like it's equal to 1 and it ends up actually being equal to 1. But if you have something else that in your, you know, algebra-trained math brains, you think that should also be 1, it doesn't actually end up being 1. And if you try equality comparison over that, you're going to end up with false. And interestingly, sometimes it'll even, like, round to 1, so it'll display as 1, but it still won't pass an equality test with 1. So generally speaking, equality tests over floating point you should never ever do. Instead, the preferred mechanism for accomplishing this task is to see if one minus the other is within a certain degree or margin of error. You would use the absolute value function abs. This doesn't give your numbers abs, it takes the absolute value. If only getting abs were so easy. That's just a little joke. So the one thing that you have to be careful with that is that you don't ask for too much precision, because if you ask for too much precision, you can see you'll eventually just it'll not work at all. However, you can see that you can carry quite a lot of precision. You can make this a very tight window and it'll still work. Like, this would be like, what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 2 more. So that's what, like, milli, micro, nano, what's the one? Pico? So it's like on the one under the pico scale, which is very, very small if you're, thinking in metric. Questions? Burp, 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 burp. Should you put my name in as Nick Moore or Nicholas Moore? I think Nicholas Moore probably my full name, but if you use, like, they also ask you for the class that you're nominating, so it'd probably be by class as much as by name, by my name, and I'm sure that people are, Femto, yes, thank you, Tyler. It's milli, micro, nano, pico, femto. There you go. I don't think it'll really matter. I think that the nominations committee, if they're tallying it by hand, then, which they probably are, then it shouldn't matter whether you call me Nick or Nicholas. But you have to do teaching evaluations? That's a good question. So with respect to the teaching evaluations, these will, I'm not sure, they'll probably be starting in a couple of weeks or so, maybe a week or two they'll open up, and it'll be an online form. They moved it to online actually even before the pandemic hit. There'll be I think it's evals.mcmaster.ca. evals.mcmaster.ca. Yes. There we go. Evaluate and make a difference. So these are not mandatory. They are confidential and anonymous, even though you have to log in to do it. That's mostly just to prevent people spamming it, right? So, there we go. So, the undergraduate evaluations are open on November 25th, so about this time next month. So there you go. And normally, with the teaching evaluations, I do tend to provide a small incentive if we... Generally, how I work it is if the percent response rate for the teaching evaluations are above a certain percent, then I will give everybody a few bonus marks on the exam or something. Just like a class-wide, here you go. But normally, I like to see at least 50% in order to be able to give that type of reward, possibly as much as 80%. We can have like a tiered reward system. And I should emphasize that I cannot see the nature of the evaluation until the final results are released after the evaluations have all been collected. So I'm not like, you don't have to rate me well in order to meet that like 50% or 80% respondency rate. It would be just like, the percentage of the class that has handed in an evaluation, regardless of as to what's actually on that evaluation. So, yeah. Anyway, I haven't really posted anything about that yet because it's still reasonably far into the future. But yeah. Anyway. Ooh, there's a good question. What are the undergraduate evaluations? Lots of questions about that. How do you determine how accurate you need? It sort of depends on your application, but something in this range would certainly be good. It depends on how tight the bounds you want are, but, it depends on how exact you want the equality. But I'd say I personally would use something in this range, just because this is too many zeros to type, basically. Do our teachers see our evaluations? Yes, but not immediately. The teaching evaluations are anonymized, so as a person, I can't... Okay, how to say? usually a few weeks into the next semester, or even a month into the next semester, I get back my teaching evaluation from the previous semester. What I see is a bunch of results that have been compiled into one document. All of the names have been removed from it, so I can't see what particular people have said about me. And, you know, this is well after all of the marks have to be submitted to the university anyway. So if everybody gave me a bad evaluation and I decided to take revenge on you guys with, marking everybody down, that, it wouldn't. The system prevents that because I don't get to see what you guys thought of me until much later after the marks have to be handed in. So generally speaking, there's like a section. So to answer the question, what is the teaching evaluation? It's a questionnaire, right? This questionnaire contains a number of rate various aspects of this course on a scale from 1 to 10, I think. It's either 1 to 10 or 1 to 5. Things like, what is the overall effectiveness of this course? What did you think of the use of technology in this course? What did you think of the preparedness of the instructor and the TAs for this course? And you can rate upon a number of different metrics. Incidentally, it's those numerical scores that are taken into account when they're determining the MSU Teaching Award recipients. The second section of the questionnaire is sort of free space for you guys to provide whatever comments you like. All of these comments are they're again broken down by categories. What did you think was done well in this course? What did you think could be improved in this course? And then like a section for all other general comments, something like that. I'm probably messing up the categories. But generally speaking, what I see is a big bulleted list of all of the comments that were received through all of the teaching evaluations. And I always make sure to read my comments from the students because they can be very informative. And, they can help me improve my teaching practice over time, which is kind of a very important point. But the other thing, the sort of, I don't want to say the real reason, because getting feedback is also really important, but like one of the primary uses administratively of the teaching evaluations is that, especially for poor, humble sessionals such as myself, hiring decisions are often made on the basis of strong or weak teaching evaluations. So you're saying if people submit a form about you, like 50% of the class, then you would do the marks thing. Yes, I will publish on Avenue like how much of each for each. We'll have a tiered system. But yeah, and it's not just about me, it's also about the TAs, it's about the presentation of the course in general, it's about the curriculum that's covered in the course. It's, there's a lot of different things that are asked about. It's not just about me. But, yeah. So, generally speaking, especially since we moved online, the respondency rate on the teaching evaluations hasn't been great across the board. So, a little bit of an incentive is a good way to get both me and the university the feedback that we need. So, I highly encourage people to fill them out once they become available, and I will even provide a small incentive to do so. We got you, Prof, don't worry. You guys are the best. You guys are the best. Generally speaking, in a normal semester, and like before they moved everything online, they would actually take 10 minutes out of class, and like I would need a volunteer to carry the forms to like a particular office in JHE, and like you would fill out the questionnaire on a Scantron sheet and all of that. The class is amazing. Thank you. It would be nice to get a full-time gig doing this. I enjoy doing it, and I think you guys enjoy me doing it, so Hopefully, anyway. Anyway, enough self-congratulations, society. Let's get back to the real stuff. Um, so, so we've talked about how floating point is inaccurate, but let's actually discuss and dissect how floating point numbers are actually represented. So, with floating point numbers, you're essentially representing things in something approximating scientific notation. Of course, the problem is that scientific notation, you are multiplying by something that's base 10. Since we're dealing with binary here, we are in floating point multiplying by something base 2. So it's like scientific notation, but you replace the 10 for a 2. That means that there are two fields that you have to represent in memory in order to be able to represent the number itself. You've got the fractional component, and you've got the exponential component. The fraction is called the mantissa, which is just a little piece of nomenclature. You'll probably never hear this word again, but unless you take scientific computation, which you'll probably take later on in your degree program. So, the exponent is represented by a certain number of bits. The mantissa is also represented by a certain number of bits. If we have 64 bits to work with, because that's the size of a floating point integer, and one of those bits is dedicated to representing whether or not the number is positive or negative, we have 63 bits remaining. There was a trade-off that had to occur. You remember last time I was talking about that big conference where everybody discussed floating point notation and the ground rules for it were set. One of the biggest things that they had to decide was what portion of a floating point number in terms of bits was given over to the exponent and what portion over to the mantissa. If you give more bits to the mantissa, that means that you can express numbers with a greater precision, right? It allows you to represent smaller and smaller and longer fractions. This part of the number becomes more accurate. If you give more bits to the exponent here, that greatly increases the range of numbers that you can represent, although the precision will become smaller. So that's the trade-off. You're trading off range for precision. They eventually decided that probably nobody's going to ever need a number larger than 10 to the power of 308. So 10 followed by 308, or 1 followed by 308 zeros, which is quite a lot, let me tell you. Yes, this is probably the case. It's worked reasonably well so far. Generally speaking, this works for the overwhelming majority of situations. If you need more range or more precision than this, especially if you're considering computing in the modern context, there are definitely other ways of representing these numbers. The only problem is they take longer, and it's not really a problem. The thing about floating point is that because the representation of a floating point number has been standardized, there actually exist inside of the CPU of the device that you're using to watch this right now, there are specialized circuits, sub-circuits within your CPU that are designed specifically to accelerate floating point calculations. These have been developed for a very long time, and in fact, if you look into the history of computing, there was at one point a very sort of obscure but at the same time major bug in Intel chips that was relating to the floating point subcircuits. So because this is hardware accelerated, floating point operations can occur reasonably quickly. In fact, one of the objective, semi-objective, measures of a computer's sort of computational power is what they call gigaflops or megaflops. You may have heard of the term megaflop. Well, flop stands for floating operation, floating point operation, flop. So, you know, it's not like it's trivial. Anyway, I might be belaboring the point somewhat. So, this is what happens sort of visually. You got 1 bit that represents the sign, 11 bits that represent the exponent, and 52 bits that represent the fraction. These are the numbers that they eventually settled on. Yes. The number of bits in the fraction limits the precision. The number of bits in the exponent limits the range. Arithmetic operations on float may lead to significant loss of significant digits. So, if we have, how many zeros is that? Can I copy paste that? I can copy paste that. Ho ho! Paste. Alright. Get out of here, you. So, you can see that when we're working with integer arithmetic, this large number, if you add 1 to it, you get that large number with 1 on the end. However, if we make this a floating point number, the 1 is lost, and we can actually even use our format function in order to view what's going on. This is literally, the 1 is literally being lost. So the 1 that's being added is sort of outside of the range of the precision of the number, and therefore if you add it to it, it gets lost. It's you know, if it's important to be able to keep that, then you want to, you know, use some sort of numerical format that is stable for those types of operations. Let me look at my questions. I wished I learned this from here before 1JC3 midterm. Ooh, you were tested on this on the midterm without it? Ooh. Oh my goodness. Lots of stuff. Thank you for your notes of affection. Just between you and just between you guys and me, I kind of feel like goodwill towards professors in general is at an all-time low, so I might be able to snag the award because nobody's gonna get nominated for anything this semester. It's a lot of the same material. Yep. FPU. Yeah, AMD is greater than Intel. Yep. Does Python use complement form to store the exponent? Python does not use anything different from any other programming language. The manner in which a floating point number is stored is not even, like, that's information that's underneath even the operating system. Like, that is kernel stuff, you know? So, actually, it's even deeper than the kernel. We're talking about hardware here. If a computing system is compliant with the, what is it? What's the name of the standard? The IEEE, where is it? Well, anyway. So the IEEE standard on floating point numbers, if your computer is compliant with it, then this is actually implemented at the level of hardware. This is not a Python-specific thing. You can assume that, like, this knowledge is applicable to every single programming language. Thank you for your votes. I feel like I'm running for office. I heard that GPU does better in floating point calculations than a CPU. Is that true? It depends on the application. So the thing about a GPU, this is a slight tangent. I can explain this quickly. So you know how CPUs these days have multiple cores? Like you might have a quad-core CPU, right? A GPU is designed, it's basically a large array of more simple CPUs, or, arithmetic logic units most particularly. A GPU might have 1,000 CPU cores, but each one of those CPU cores is very, very simple. So for particular types of calculations where, and this is something that you guys are going to see in 3rd and 4th year, you have particular types of applications that are called embarrassingly parallel. These are certain types of things like matrix calculations, the types of calculations that go into rendering three-dimensional environments, for example, are embarrassingly parallel applications. This means that you can take a single calculation and split it up amongst all of those 1,000 CPUs that are inside of the GPU, and that can drastically accelerate the speed with which you can perform those calculations, and in fact keep up with something very computationally expensive, like rendering what's the new video game that they it's Crysis. Crysis is the stress test these days for GPUs, right? Just hit my tooth with the cup. Anyway, so that's how a GPU works. It is a large number of more simple CPUs that they're not as general purpose as a CPU, like like your Intel Core i5, like I've got in this very old laptop. It accelerates it by splitting up the calculation. And incidentally, the GPU will also use the same floating point format as everything else. Does Python use complements to store? Oh yeah. So yeah, I believe the exponent is stored in 2's complement. If we vote for you, can we get a fun "I voted" sticker? I guess. I don't know. Maybe I can make a custom emoji. I don't think you can make custom emojis. Yeah. I don't know. We'll see. Anyway. So. I'm going to run up on a platform of not destroying you. Vote for not destruction. There we go. Anyway, so, given that floating point has all of these problems, it would be nice if we had some alternative mechanism if we wish to perform more exact arithmetic. In Python, we've got 2 basic approaches to this. Excuse me. We've got the decimal library, and we've got the fraction library. So, in order to import and use the decimal library, you from decimal import decimal with a capital D. The decimal library produces the same errors as you would produce by calculating things by hand. And the sort of big secret to how it's able to perform better than floating point representations for the same thing is that it sacrifices both memory and runtime in order to be able to represent things more accurately. There are some tricks, though. So if we import from decimal, from decimal import decimal, if we write decimal of 1, then that's 1. If we have the decimal value of 0.1, however, you can see that the decimal value that's being held is including this floating point error again. So the reason for that is because you're feeding into the decimal library something that's already floating point encoded. If you want to get around that, encode it as a string. So if you were to take decimal of 0.1 plus decimal of 0.2, you can see you get 3 point all this garbage, all of this smelly, smelly garbage. However, if you enclose these in, if you make those into strings, you can see that it is calculated according to the manner in which we would expect it to be calculated. So there you go. The decimal library. So why wouldn't we use this all the time then? And the answer is these calculations are much slower than floating point operations. I'm not going to do this because it requires being in the Jupyter Notebook environment, and, you know, we need to just keep moving. But essentially, if you are performing regular floating point arithmetic versus performing things on the decimal library, you're paying about at least 3 times the runtime to perform the same calculation. And while this is, you know, we're still talking about small fractions of a second here, the point is that these very small increases in runtime, if performed across very large numbers of calculations, will result in, like, visible or, you know, noticeable lag in terms of runtime. Kind of similar to the Fibonacci example, right? In the Fibonacci example, we were performing a very large number of very quick operations, but the largeness of the number of operations eventually outweighed the smallness of the time for each individual operation. So let me see questions. Bitmojis with I voted stickers, yes. If we vote for you, can we do C for the rest of the course? Oh! I wish. I wish so badly I could teach you C. I think that C should be the language that you learn in first year. But, you know, that's just because I'm kind of I'm a mechatronics guy by background, which means that, like, hardware is, like, I love hardware, and, like, for those of you who aren't familiar with the mechatronics program, a lot of it is sort of learning about the interface between hardware and software instead of just staying in software land or just staying in hardware land. How do we vote Mark for a TA award? If you look at the link that I provided, there are 2 links on that page. One is vote for a professor, the other is vote for a TA. So I would imagine you just use his name and vote for him. Yep. Do you know what languages you'll learn this year or next? No. Not off the top of my head. I'm downright convinced that you guys are going to have to do C at some point. Because if you guys make any serious study of operating systems, which I imagine you will probably do, then you're going to have to learn C. C and Elm, okay, yes. SQL doesn't really count. I mean, it does, but it doesn't. It's kind of like how HTML doesn't really count. Yeah. Is C worth learning for a non-CS student looking to build their resume? See, it's a bit more niche, is the thing. If you're learning C, then you're learning how memory works. It'll certainly make you a much better... assembly, yay. It'll make you a much better programmer, because you'll have a much better conception of how memory works in the computer, which means you'll be able to use it more efficiently. But I would say, generally speaking, many of, like, if you're looking to get a job programming, if you're looking to get a job C programming, that's a very specific type of job, right? However, like, if you're making, like, an academic study of programming in general, I do recommend C, but I would say if you are a non-CS student looking to build up your resume, I would focus more on the more directly resumeable skills, if that makes sense. That means studying some of the major C is a major language, but most of active development is normally occurring in things like Java and C++. Lots of people want database stuff these days. Database applications are really big these days, so I would highly recommend learning a relational database language like SQL, and we're going to learn a little bit of it. But yeah, web dev is another good one. If you learn to use HTML and CSS, then that's, excuse me, normally most people who went to university to study computers look down on their noses at jobs doing web dev because it's not considered sufficiently abstract for them. But, you kind of got to tailor your skills to the market a little bit, Yeah. C++. So, if you want to learn C++, there are a lot worse places to start than learning C, because C is the incremented version of C++. If you understand C, then you're already halfway to understanding C++. Although, to some degree that's not true. There's a lot more in C++ than there is in C. But, the memory management system, that's, directly out of C. So, there you go. You got to put on a team depending on your skills unless you apply for more specific jobs. Yeah, so, yeah, I don't know. It really depends on the type of job you want, C++ is C with classes. Yeah, but, inheritance and polymorphism aren't by any way trivial concepts. Yeah. If you guys are interested in dipping your toes into C++, by the end of the semester, I'll have some lectures on C++ up on for the other class because we have to cover it a little bit. Yeah. There's a thing called full stack development as well. There's this is a reasonably sorry about going off on this tangent again, but there's a reasonable full stack development skills tree, I think. There's this skill tree that is, yeah, this is it. So this is as of 2018, but I think it's probably still pretty applicable. Let's see here. I want the image. Thank you. So, learn the basics, HTML, CSS, and JavaScript. Getting deeper into JavaScript, there's all of these guys, right? This, if you're looking to become a full stack developer, this is more angled towards web applications for sure, but this is one roadmap that you can take. But yeah, I don't know. We need to get back to the topic at hand. Yeah. C++ is definitely a good one to have. C++ is considered a difficult language, and it, there are jobs for C++ programmers. There are always jobs for good programmers, no matter what you program in, unless you program in Haskell, snark snark. But if you know C++, then that's a good employable language. Java is also like that. Anyway, so decimals. The other thing that we can have is fractions. So the fraction library actually stores two numbers and represents the ratio between two numbers, because that is what a fraction is. So because it's storing things as the ratio between two numbers, it's actually stored somewhat, it's stored in a manner that can represent, it represents with exact precision rational numbers that cannot be expressed by a finite series of decimal places in any base system. Like 1/3, unless it's base 3, but whatever. So, from fractions, import fraction. Fraction 1 divided by fraction 3, fraction 1/3. You can also just write it as fraction 1/3. So fraction 1/3 times fraction 7/10 is 7/30. So there you go. And I think it reduces as well. Let's see. Yeah, it reduces fractions automatically for you. Ha-ha! So there you go. So if you need to represent a rational number, I recommend the fraction library. Normally, if people are trying to replace floating point and get better precision on floating point operations, generally speaking, we go for the decimal library because it's just a more direct substitution, but it's important to know both exist. So, in summary, what do we do about floating point? Number 1, avoid uses of it. Use integers instead and compute with whole numbers rather than things that are smaller. So if you have to represent, 1.73 meters, do it as 1,730 millimeters. That's, you can kind of just move the decimal point over until you don't really have to worry about the fact that it's a fraction that it's a decimal anymore. Use the decimal or fractions standard libraries instead. They are slower, particularly for very large and small numbers, but your results will be accurate. Use a library for interval arithmetic with float. This gives safe lower and upper bounds, but it takes twice as much time and memory. Use a problem-specific library with a check the literature for algorithms with known numerical properties. For example, solving differential equations. This is more work than just using decimal, but that's okay. Use symbolic computation in computer algebra systems instead of a programming language. So that's kind of an interesting one. If you load up something like MATLAB or Maple, these types of systems will have libraries that allow you to perform calculations on symbolic arithmetic, which essentially means that you can get your computer to do your algebra for you, and even tough things like calculus. So yeah, that's always an option. When using float, never compare for equality. Check your result within a tolerance. Very good. So, there we go. Let's talk about approximation algorithms, see how far we can get through this. Y'all remember our old x-intersect problem, where we have the interval upon which we are looking for the x-intersect of a monotonically increasing function, and we narrow that interval based on whether the midpoint is above or below y is equal to 0. You guys remember that? I hope so. We revisit the problem. Can we take the exact x-intersect by setting the epsilon equal to 0? Just to remind you guys, the algorithm would narrow the window represented by the bounds a and b by half each time for each step in this algorithm. It's actually very similar to the binary search algorithm. However, this algorithm is configured to stop when that interval is smaller than some epsilon, some error value. So the question that we asked at the beginning of this course is, if we set that epsilon equal to 0, would we be able to find the exact x-intersect? And the answer is, of course, absolutely not. At least not in most cases. if you're in a very, very particular case where the x-intercept happens to fall precisely onto one of the, shall we say, one of the m values that's eventually calculated throughout the course of that algorithm, and that m value actually tests equally to the floating point, if you manage to dodge the floating point equality problem as well, then you might be able to get away with this. But in most cases, you won't be able to. In fact, in most cases, what's going to happen is that you will eventually hit the point where you'll be flipping between two very, very small numbers, because the number that's represented by the actual x-intercept is between two floating point values. So another way of thinking about floating point is an analogy with electron mass or electron charge. Let's go with electron charge. We know from physics that no charge can exist that's not some multiple of the electron charge, right? Because electrons have one specific fixed charge. That's the charge quanta, or quantum, right? That's the idea of a quantum. The floating point arithmetic also has a quantum, and that's the smallest floating point number that it's possible to represent. Everything must be a multiple of that value. So, if your function falls on a value that's between those two values, then the function is either going to oscillate between or just continuously return one of those, and you'll never actually reach the x-intercept. And probably what would happen is that your program would go into an infinite loop, and it would never terminate. So there you go. Let me just take some questions. Could you use double instead of float? Yes, you could make. So what a double is it's a double precision floating point number. So float. Let's see. Where is the Googs? Google. Floating point versus double precision. So this is in C++, but it's very similar. Is there a library that makes floats more accurate? Yeah, the decimal library. Do we have a test this Saturday? Yes, we do. Yeah, you should be able to use a double in. Again, doubles are defined in the operating system and the hardware, not at this level, so they will be available to any well-supported language. The double has twice the precision compared to float, which means the double data type has double precision. Yeah. So it's possible that we have been talking about doubles, because this is saying that double is 64-bit and a float is 32-bit. So it's possible everybody's already moved to double. Anyway, for more information, please check your local library. Cool. Anyway, I think that's as much as we can cover today. So thank you very much for listening in, folks. I hope that you guys aren't stressing out too much about the test. Don't worry too much about it. But yeah, anyway, I got another class to get to, but we still have 1 minute remaining, so I'll take any questions that you might have. her easy, folks. Don't do anything I wouldn't do.